So, greeting to everyone, all the participants. So, this is that files which we have discussed. These are data which we discussed, starting from basic till pair sample t-test we have discussed. Just now, one of the participant, madam, has asked about data duplication, how to check. I'll first show that one, and later we will go for the next topics. Okay, I'll select one file. For example, we have, let me say, let me take demo file once again. In this demo file, how we are checking duplication is we are going to go to transform data. In data, identify duplicate cases, right? So what are the files which you want to check duplication? For example, I want to check, I'm taking randomly some variables, few variables. I'm carrying from left side to right side. Okay. And click OK. Once we click OK, system will show valid 6400 because in this file we have 6400 samples are there. You see here, observations wise, we have 6400. So the same thing system is showing here, 6400. Now in this, within this, duplications 35, primary cases 6365, and the total is 6400. Hello, madam, you got it?
Yes, sir. Yes, sir. I think I'll just have to check again on my Spss file.
Yeah, there is some mistake, or you must see the files actually, how many observations you have. You may be having 440 observations. That's why system is showing you 440 observations.
Okay.
Right. So I'll close this one. Now we'll start with the data.
Sir, I have another question.
Yeah,
Thank
please
you,
ask.
sir.
This is regarding two questions actually. One is regarding this missing data.
Okay.
I note that using this using in under SPSS, if you go to analyze, there is a.
Do you want to identify the pattern, or do you want to input the data?
Identify the input the data.
Okay, imputation. Imputation, we can do it, sir. We must go to analyze. In analysis, if you want to do mean substitution, there's a different method. You must go to transform. Here you must do replace mean values, missing values. For missing values, you want to transform, replace missing value. Here, wherever you have missing value, for example, gender you take, and here you are not gender. Let me take some scale data. Some data. Okay. And here you can see it is going to miss placed by series mean.
Okay.
So click once OK. Wherever there is a missing, it will take the mean value of that particular variable, and it is going to substitute the mean value in that variable with a new variable name. PD, for example, I'm taking PDC. Now it is going to become PDC underscore 1. Okay. This is for mean substitution. For example, you want to do regression imputation, you must go to analyze. In this missing value analysis, and in this, if you take any variable, for example, let me take again the same PDC and some other variables. Now here you are going to select what type of estimations you want to do, regression, or you want to do EM value. You can select it.
Okay.
Right, so that's it. Once you select this one and you select the variable, whatever variables you want, or you want to regression, you are going to specify here where you want to save the file. You give the file name and click continue. Automatically, you're going to get the regression imputation in that particular variable.
Okay.
Right, sir?
Okay, there was something about maximum likelihood also, right?
Yeah, that's EM. EM is the same thing. For in EM method, it will first do regression and later do maximum likelihood.
Okay.
Because yesterday I showed the file. I think PPT I showed you. Just a moment. Missing.
That's okay. I got it. Just wanted to know because there I saw two missing values. That's why
we have this one. You can see this one. Just I showed the last file. Here you can see, not this one, this one. Yeah, you can see this one, maximum likelihood. It does first the regression and later it does maximum likelihood estimations.
Okay, thank you, sir. One more question.
Yeah.
I wanted to check how, can you show me again how to check for normality?
Normality, okay. Okay, let us take this file. Let me take a file which you have scale data. Yeah, for example, this marks variable is there. We want to check normality of this marks variable. You must go to analyze. In analysis, you must go to explore. In explore,
okay, explore. Okay.
You must select the marks, which variable, whichever you want to check. You select this one. And here you can go to plots. In plots, select the normality of plots with the test.
Okay.
An histogram for a diagram purpose. But this is a setting which you need to select in plots. Within the plots, if you select, you will get normality. Now click continue and click OK. Once I click OK, we will get the test. Yeah. That's right.
Sorry, last question. If I have a large sample data,
how much? Large sample is how much?
Around 500.
500 is not very large. Okay, please say.
Okay, like maybe I can even increase it to 1,500 because it's all finance only.
Okay, sir.
All I wanted to ask was that if I do the normal test and I come see that it is not normal, then what should I do? Because
same thing we said. No, you say that according to central limitation theorem, when the data becomes large, tend to be normal.
Okay, so there is no other test that I can do instead of that, right?
No, we cannot make the data because see, when you're talking about opinion-based research, generally in opinion-based research, never data will be normal distributed.
Okay.
But when you're doing structure equation modeling with the covariance-based software like AMOS, one of the important assumption is data should be normal distributed. But thousands of research are submitted on AMOS, and these people are not checking anyway normality, how they are able to submit the thesis for national, international journals and universities.
Okay, thank you, sir.
Yeah, that's only the evidence, because what we are doing, we are just having a reference. Okay, how somewhere these people are submitting, right? So they are, when I see they are writing the same thing, saying that central limitation theorem wise, they are getting exempted from that normality test.
Okay, thank you.
And here we have tests, test of normality, Kolmogorov-Smirnov and Shapirovik's test.
No, that I saw, that I remember. I forgot how to even go to the test.
Navigation.
Yes.
Navigation step. Now we'll start with the actual data. So we will discuss chi-square test. And after chi-square, we will discuss today about one-way ANOVA, one-way repeated measure ANOVA, two-way ANOVA, and MANOVA. As time permits, we'll see whatever is feasible, we'll discuss to the extent possible. So first we will discuss with the chi-square test. Why I'm taking chi-square? Because in non-parametric methods, the important test is chi-square test. And in chi-square test, we have dependent and independent. Both must be categorical. Both must be categorical, whether it is dependent or independent. And when you want to see, is there any significant difference between these two categorical variables, we must use chi-square test only. So that's why most frequently people use, researchers use this chi-square test. Let me show you one example here. This is related to cancer data, where we want to see, is there any significant difference between gender to tumor budding, TB. So we want to check whether there is any sort of relationship between gender towards a tumor budding. If you see gender, we have two types of genders here given, male and female. And coming to TB, there are two types of, three types, BD1, BD2 and BD3. So the objective, the null hypothesis is, we can state there is no significant difference between male and female towards tumor budding. So this is the null hypothesis which you need to state. After making the statement of null hypothesis, we can go to analyze. In analysis, we can go to descriptive statistics. In descriptive statistics, frequency, crosstabs. In this crosstabs, now we said dependent and independent. Generally, we take independent variable as rows, gender, and the dependent variable will be taken as column. And after taking gender and column as tumor budding, we can go to statistics. In statistics, we have this check button, chi-square test, and click continue. And in cells, we must select expected and rows, because we want to see in terms of male and female. So we need to select this percentage by rows. We don't need any column. We don't need this column. We only need these rows. And click continue and click OK. Now we can see here total 129 sample. There's no missing data in this. But if you see gender, tumor budding wise, you can see male wise 76 people are there, female wise 53 people are there. And we can see this also frequency distributions, cross tabulations we can see. The important thing is chi-square test. In this chi-square, we need to see this Pearson chi-square value. And you can see this asymptotic significant value. The significant value what we got here is 0.869. 0.869. If this value is less than 0.05, we are going to reject the null hypothesis. So in this case, we are accepting the null hypothesis, and we made a statement, the null hypothesis, there is no significant difference between gender towards a tumor budding. Is irrespective of gender, the tumor budding is happening in the patients, because the significant value is 0.869. And one important thing, you can see this is asymptotic significant. Can anyone say what is the difference between significant value and asymptotic significant value? Hello? Hello?
Sorry, sir, I don't know.
Yeah. Any other participants? If they want, they can say asymptotic significant and significance. See, asymptotic in the non-parametric test, system will not calculate with actual value. It will increase the sample size and create the values. So that's why it is resemblance of asymptotic. Generally, if I have 20, 30, system cannot do analysis calculation with the 20, 30 variables, the observations. So it increases the number. That's why it is called asymptotic significant value. There's no problem. We can use this value also. We can note in the research also. But you need to understand what is this asymptotic significant value. It is resembling significant value, not the exact value. If you see this parametric test, we don't get asymptotic. We'll get the exact significant value. But in non-parametric methods, when you are doing, we'll get asymptotic significant value. Okay, this is very important point to be noted. And one more important point, when you are doing chi-square test, in the cross tabulations, where in a cell, if the expected count is less than 5, if it is less than 5, then we cannot use this Pearson chi-square value. This is a very important point, and many people submit the thesis also in the same way, this cross tabulations, chi-square, without checking expected count. You need to always see the expected count in the cross table. Hello?
Can you repeat this, sir?
Yeah. You must, in a cross tabulations of chi-square value, you need to observe the expected count. You can see the expected count here. For male to BD1 is 37.1. Here 20.6. Here 18. Right? If this count is less than 5, we cannot use this Pearson chi-square test. We cannot use this Pearson chi-square test. we must use a Fisher exact test must be used. Fisher exact test must be used. Because if this count, expected count, because people will not calculate this exact count, they simply do the analysis and submit. So that is a mistake they are doing. When you have this count less than 5, here fortunately we don't have that value less than 5. In case you are having less than 5, we must not use Pearson chi-square value. We must use Fisher exact test. Okay, I'll take one data and I'll just show you Fisher exact test. You can see this data which is related to exercise and heart disease. Exercise and heart disease. Exercise, we have given values like 1 and 2. 1 stands for they are doing exercise. 2 means they're not doing any exercise. And heart disease, 1 means presence of the heart disease. They have a heart disease. 2 means they don't have any heart disease. We want to check where there is any sort of relationship between exercise to heart disease. We must first create the null hypothesis, write the null hypothesis stating that there is no significant difference between exercise and non-exercise towards heart disease. We are saying there is no relationship between exercise and heart disease. And we need to do the analysis, analyze in this descriptive statistics and crosstab. Here, dependent should be column, heart exercise should be row. Always independent should be row and the dependent should be column. Now in statistics, select chi-square value, click continue. In cells, we need to select this expected. This is important. And select rows. Click continue and click OK. Now, if you see the output, in the output, first we'll see this exercise into heart disease cross table. You can see this expected count 3.1 here. It is less than 5. And even there, even for exercise, people are not exercising also, we have 4.9. So when you have expected count less than 5, we cannot use Pearson value. What you must do is, you must use this Fisher exact test value must be used. So here you can see Pearson chi-square value is 0.014. It means we are rejecting null hypothesis and stating that there is a relationship between exercise to heart disease. Okay. But when you're talking about Fisher exact test, you can see the significant value is difference. It is 0.033. Okay. So when you're writing, you need to write this value as significant value, not the Pearson chi-square value. Fisher exact value, exact test must be used. This is 0.033. Of course, conclusion is the same thing we are getting, that there is a significant relationship between exercise towards a disease, heart disease. Am I clear? Hello?
Yes, sir. Yes, sir.
You can read this one also.
So there's a question here.
Yeah.
So what difference did you make? Actually, you went to analyze only, and from there, sorry, cross tabs only you did it. The minor changes which
here statistical package has become intelligent nowadays. It is creating automatical. We are not selected any extra option of Fisher exact test. Hello? Hello? We have not selected any extra settings. System did automatically, and the system specified here 2 cells, 50% has expected count less than 5. So system automatically has given, in this case, Fisher exact test. In the earlier case,
so as in,
system,
by default, it will give, if the count is less than 5, it will give you Fisher exact test. If it is not, it will not show the Fisher exact test.
Yes, because Spss is having, yes, correct, absolutely correct. Spss is a bit intelligent. It is automatically detecting that value and giving Fisher exact test in case if we have expected count less than 5. Okay. A system will automatically do. We are not going to do any sort of setting. Only thing we must see is You must not write when you have exact Fisher exact test, you must not write this PS and chi-square value, but you must note this value. That's only
Right,
the important.
Thank you,
Right.
sir.
So this is all about chi-square test. Anyone have any doubt, participants, they can ask. Yeah. Now we'll go for the next topic. Now from here we'll start
Sir,
ANOVA test.
sir, can you hear me? Can you hear
Hello?
me?
I can hear you.
Hello?
I can hear you.
Hello, can you hear me, sir?
I can hear you, sir.
Sir, all of this can be done with Python or not?
Yeah, we can do with Python. There's so many packages are there in Python. We can do that with that.
All of it, right?
Yeah, majority, because it's open-ended. A lot of people are adding. Majority test we can do.
Yeah.
Now
Okay,
we have
thank you, sir.
Python integration with SPSS also. We can do with Python. But you must check, sir, does not mean that every test can be done. You have to check what type of class they are calling and how they are doing that analysis. Okay, shall we go ahead? Now we'll discuss with the one-way ANOVA. Yesterday we are discussing about different type of statistical methods. I just shown one PPT. I'm just seeing where it is. Yeah, just open this one. Yeah, you can see this one. When we are going to use one-way ANOVA, we are going to use one-way ANOVA. The same conditions where we did two independent sample t-test. Only the difference is in the independent variable is having more than two levels. If it is more than two levels, then we are going to use one-way ANOVA. So ANOVA is same like a t-test. The only extra condition we are going to have is the independent variable, we are going to have more than two levels. If you are having exactly two levels, we are going to use two independent sample t-test only. But if the levels are more than two, then we must use one-way ANOVA. All conditions must be fulfilled, like a dependent variable must be scale data, and they must not be, and they should be normally distributed. Independent variable must be nominal variable and having more than two levels, and they are independent, and they are also independent. In these conditions, we will be doing one-way ANOVA. And please understand, independent variable is only one. If the independent variable are two, if the number of independent variables are two, then we will be doing two-way ANOVA. In one-way ANOVA, we have only one independent variable, but in two-way ANOVA, we'll be having two independent variables. Dependent variable, in all the cases, we'll be having only one and one. In case a dependent variable is going to become two, we are going to do MANOVA. We are going to do MANOVA test. And when we do repeated measure ANOVA, same like one-way ANOVA, but only the difference is that in independent variable, the property will become dependent. If the variables, the levels are dependent, then we are going to do a repeated measure ANOVA. So this four we are going to see one after another. One-way ANOVA, repeated measure ANOVA, two-way ANOVA, and MANOVA. These four things we are going to see sequentially. Anyone have any doubt, you can please ask, but please remember these conditions under which we are doing the analysis. In all cases, yeah.
Sir, what this level indicates, sir?
Level means, for example, male and female, they are levels.
Okay.
Okay, for example, age groups, we are saying less than 20, 20 to 50, 50 to 70, and above 70. These are called as levels. Okay, when you have more than two levels, we are going to do ANOVA, exact two levels. T-test, we are going to use T-test. Okay, and you must see the property of nature. If they are independent, one-way ANOVA. If they are dependent, repeated measure ANOVA. And you can see independent variables. If there are two independent variables, we are going to use two-way ANOVA. In case dependent variables are two, then we are going to use MANOVA test. So under these conditions, we are going to use different type of test. Always you can note one standard in thing, independent variables are always nominal only. And in the dependent variable, always dependent variables are scale and normally distributed. So let's go with the analysis. First, we will do one-way ANOVA. I'm looking for that they have file. Just a moment. There's a file. Okay, let's take grade file and we'll do it instead of wasting time. Right. Now we want to see where there is any difference between ethnicity to final marks. If you see the file, ethnicity is a variable, independent variable, and here we have 5 levels: native, Asians, blacks, whites, and Hispanic. These are the 5 levels we have. This is independent variable. Ethnicity is independent variable. Dependent variable is final marks. So we want to see, is there any relationship between ethnicity to final marks, what the students are scoring. So we need to create one null hypothesis saying that there is no significant relationship between ethnicity to final marks. Or we can say there is no significant difference between the ethnic groups towards final marks. And here, dependent variable is a scale data. And we are expecting that it should be normally distributed. And independent variable is nominal data and having levels. And one important thing, can independent variable be an ordinal data? Can independent variable be an ordinal data? Hello? Hello?
No, sir.
No, sir.
Yeah, that's important point. Independent variable cannot be ordinal data. It must be nominal data only. That is important point. Dependent variable cannot be nominal, cannot be ordinal. In case if it is nominal or ordinal, you must use non-parametric method. Okay, Kruskal-Wallis test must be used in that case. Kruskal-Wallis test, non-parametric. So the dependent variable must be only scale data, and imagine that it is having normally distributed. Assume it. Now let's start the analysis. Analyze. And in this, compare means one-way ANOVA. Now ethnic group is taken as a factor, and the final marks we can take it as dependent variable. That's it. At the moment, we're not going to do any setting. Simply click OK. We have taken dependent variable is final marks, and ethnicity independent variable is taken as factor. Click OK. Now here, this is ANOVA result. You can see the significant value is 0.540. If the significant value is less than 0.05, we reject the null hypothesis. Since it is more than 0.05, we can conclude that there is no significant difference between ethnic groups towards final marks. Means whether it is a native or Asians or Hispanic, they're not nothing to do with the marks what they are getting. So this is a significant value. Significant value 0.540, which is greater than 0.05. So we are accepting the null hypothesis. This is the way we are do ANOVA test. Now further, in case if it is significant, in case. Now how to check between the levels? I want to check native to Americans, native to Hispanic. Then we must use post hoc test, which is called as multiple comparison. You are going to do comparison between the levels. For that case, again, we must go to analyze. In analyze, compare mean. In compare mean, one-way ANOVA. Here we must go to post hoc test. In post hoc test, okay, Now we are expecting that data is having equal variance. By default, if you don't have any sort of review or literature review or anything saying that this post hoc test must be used, you can use Tukey method. Generally, people use this Tukey method. Some people in construction industry or some other industry, they say Bonferroni method. Okay, until and the scholar specifies or they read some literature, this particular post hoc test must be used. We must use this Tukey method. Some people even uses Duncan also. It all depends on the literature which you read, basing on the research area which you are taking. Now here we are using Tukey method. Click continue. Now click OK. Now in this case, I know what is already we discussed. There is no difference. But in case if we have significant difference, how to check multiple comparison? Here you can see the multiple comparison between native to Asians, native to black, natives whites, natives and Hispanic. And you can see the significant values here. If the significant value is less than 0.05, we conclude there is a significant difference between the levels. For example, here instead of 0.940, we are having 0.05. Then we can say there is a significant difference between natives to Asians. Natives to Asians. So in this way, we can check the values where we have any sort of difference between levels. Multiple comparison test. We are using Tukey method. If you want to see what is and how much is the value for natives, what is the value for Asians, you must do one more setting. In analysis, compare mean, one-way ANOVA. You must go to options. In options, you must select descriptives. If you select the descriptives, here we are going to get clearly the mean value for each level in terms of marks. You can see clearly that these blacks and whites are getting marks. No, Asians are having more marks, 62.85. Natives are having less marks, but the difference is not significant. So this is all about one-way ANOVA.
Hello.
Anyone have a doubt? They can ask it.
Yeah. So able to hear me?
Yeah, I can hear you.
Hello.
Yeah, I can hear you.
So actually, I had a request, sir. So when you are maneuvering through the analysis part, and when you click on certain buttons, so just please momentary, you can take a pause currently, because I think I am actually doing it on.
You want me to go slowly? Hello? Hello? Yeah, do you want me to click the button slowly?
Slowly, yes, exactly, sir. Because from where you are maneuvering, it will be a bit difficult to catch it. Thank you, sir.
Correct.
Perfect. Totally that. Thank you, sir.
Yeah, I'll just show you once again, like in analysis.
Thank you.
Yeah, compare mean in ANOVA. This is a navigation path. In this navigation, we have selected dependent variable here, independent variable here. And post hoc, we have selected Tukey, this one, and I click continue. And for descriptives, we have selected options. In these options, we have selected only descriptive value. Once you click continue and click to OK, you are going to get this output values. Now we'll discuss one-way repeated measure ANOVA. In one-way repeated measure ANOVA, independent value, the levels will be dependent property. For example, yesterday's case I was saying at Corona time, they conducted a what you call a yoga type of program, meditation type of program for the medical people. So they are seeing the stress level in this medical people before conducting this meditation program and immediate after the program, and they have taken the stress level after 1 week and after 1 month. So 3 times they have taken the stress levels of this medical people in 3 times. before the program, immediate after the program, and 1 month after the program. So when you want to compare, is there any significant difference between stress levels at 3 times? Then we are going to use repeated measure ANOVA. When you are doing only 2 times, we can use paid sample t-test. We are doing 2 times, like we want to do before program stress level and after program stress level you are doing, we can use only paid sample t-test. But when you are doing 3 times, the researcher want to test before program, what is the stress level? After conducting the program, immediately, what is the stress level? And after 1 month, what is the stress level? So 3 times the researcher want to understand what is the stress level. Is there any significant difference between the stress levels? Then you must use one-way repeated measure ANOVA. One-way repeated measure ANOVA. We'll take one example here. This is a simple example. Let me close other files. You can see we have around 15 students are there, and these 15 students got their exam marks based on 3 methods: method 1, method 2, and method 3. And I want to see, is there any significant difference between the performance of students in the 3 methods, like method 1 compared to method 2 compared to method 3. Then we must use repeated measure ANOVA. Repeated measure ANOVA must be used. Am I clear? Hello?
Yes, sir. Yes, sir. You're
Yes,
clear.
sir.
Can I go ahead?
Sure, sir.
Right. So we are doing repeated measure ANOVA when we have same data, like the same student, 101 roll number. We have taken with method 1, how many marks they got in a subject. With the method 2, how many marks they got. And with method 3, how many marks they got. Same student, 3 times we are testing. So in this case, we will be using repeated measure ANOVA. So let's start the analysis. Analyze. In analyze, you must go to general linear model. General linear model. In this general linear model, we must select repeated measure. So analysis. Earlier, one-way ANOVA, we were taking compare means. But for repeated measure ANOVA, we must select general linear model. In that, we must select repeated measure ANOVA. Repeated measure ANOVA. Now, in this repeated measure ANOVA, we want to test the difference between methods. So let us name it as methods. How many levels we have? We have 3 levels. 3 methods are there. So enter the name of the method, like you write it methods, and number of levels are 3. Click add. Once I click add, we'll be getting methods 3. And after doing this, we can select a define. Click a define. Now, after clicking define, we must select each method and click this right button. Select each method and click this right button. Once I click this right button, we'll get that method to the right side, like method 1, method 2, and method 3. So method 1, method 2, and method 3. Now in this, we'll select the options. We'll select the descriptives. And you can see I have selected options only button, options. Click descriptives, click continue. And in plots, we can select these methods. I selected these plots, method to horizontal. Click continue. Okay. After entering here, you click add, you get methods and click continue. Now we can do other settings also, but as of now, we are clicking OK. So that we are directly going to the analysis screen. Yeah. Now this is the output screen. In this output screen, you can see the three methods and the descriptives also here. Method 1 marks are 61.20, method 2 marks 77.00, method 3 83.27. So there is a difference between three type of marks. Directly let us see this mutual test of spacity. Now, anyone knows about this spacity test?
No, sir.
Yeah,
No.
because when you're doing the spacity is one of the important tests that need to be done before going further to understand the results. Now, spacity, just I have a PPT, I'll just show you the PPT. Mucini's test of spacity is a statistical test used in the context of repeated measure ANOVA. It assumes where the assumptions of spacity is met. First of all, what is spacity? Spacity is assumption that variance of the differences between all possible pairs of within subject conditions are equal. In other words, it assumes that variance of the differences are equal for all pairs of conditions. This is called spacity. Very important assumption for this parametric test, especially for this one-way repeated measure ANOVA. Spacity is very, very important assumption. What it is saying is, when you have the data, system is trying to take the difference between method 1 to method 2. It will take the difference like 60 minus 70 minus 10. 56 minus 78. It will write all the values, it will write as one variable. And it will take the difference between method 2 to method 3. It will create one variable. And method 1 minus method 3. It will create the third variable. Now, we have three variables, where each is a difference between the two methods. Now, for each variable, system will identify the variance and is assuming the variance is equal between the differences. If that assumption is satisfied, it is called spacity is there between the data. I hope you understood what is spacity is. Spacity is a difference between, is a variance of the differences between the methods. System is going to calculate the difference between method 1 to method 2. It will create one variable. Let us say, for example, x1 variable is created. Between x2 to method 2 to method 3, it will create one variable called x2. And between method 1 to method 3, it will create a variable called as x3. Now we have three variables, x1, x2, x3. Now system will take the variance of each variable and assumes that the variance is equal between x1, x2, x3. If that is the case, it is called spacity. So the same thing it says, spacity is the assumption that the variance of the difference between all possible pairs of within subject conditions are equal. In other words, it assumes that the variance of the differences are equal for all pairs of conditions. So the spacity should be there. If the spacity is not there, we cannot go further and interpret the results. And the null hypothesis is the variance of the differences between all possible pairs of within subject conditions are equal. Means spacity is not violated. Spacity should not be violated. We must not reject this null hypothesis. We must accept this null hypothesis. If this null hypothesis is accepted, then only we are going to go further into the discussion of the results. So spacity is not violated. There's a null hypothesis. We need to accept this null hypothesis. The variance of the difference between all the possible pairs of within subject conditions are equal. Now let us see the value here. Now this is Muccioli's test of spacity. You must see the significant value. This value you must see, right? And this value you can see it is how much? 0.112. This value is more than 0.05. So we are accepting that spacity is not violated. Violated means spacity assumption is accepted. There is a spacity. Is there? Spacity means the variances of the difference between the pairs are equal for all the pairs. So this is what is very important. Further, it is there. Lot of discussion is there. Only thing is, if I discuss in more detail, you will get confused and you may miss somewhere. Okay. So only understand when you are doing this repeated measure ANOVA, you need to see this spacity value. And this spacity value, significant value, must be greater than 0.05. Then it means the spacity is not violated. Here you can see they have written a very big statement. But what I shown that will be very easy one to understand what is spacity. Anyone have a doubt at this moment? They can ask. Hello?
No, sir.
You can go ahead.
Yeah, sir, sure.
Well, can I expect that everyone understood what is spacity?
Yes, yes, he clearly understood.
Yes, spacity is one of the assumptions that need to be satisfied. In case if the spacity is not satisfied, then we must do corrections are there. There's a different story again. But in this case, spacity is now accepted. So we're not violating the condition of spacity. And after that, if that is accepted, then only you need to come to this table, which is called tests of within subject effects. Test of within subject effects. In this, we must see, in methods, we must see spacity assumed, because we have accepted that. If you're not going to accept it, then we need to do some corrections for that. That's a different aspect. In this case, spacity is assumed. Now we need to see only significant value. Significant value is 0.000, which is less than 0.05. It means we are rejecting the null hypothesis. What was the null hypothesis? There is no difference between methods in terms of student performance. But here it is rejected. It means there is a difference between method 1 to method 2 to method 3. There is a difference between the methods. So significant value less than 0.05. We are rejecting the null hypothesis. So this is the conclusion of what we call one-way repeated measure ANOVA. We can discuss all these things. A lot of discussion is there, but just I want to make it interesting and easy to make you understand. You can see method 1, method 2, and method 3. Method 1, we have very less performance in marks. Method 2 is in the median, and method 3 is having high performance. So there is a difference between method 1 to method 2 and method 3. So this is a conclusion of one-way repeated measure ANOVA. Important point is you need to first see this as spacity. In case if it is not significant, you must go to these methods, and accordingly you must see the values here. Right.
So
Anyone have a doubt? They can ask at the moment. If not, we'll go for the next topic.
Hello. Hello.
Yeah, hello.
Yes, are you able to hear me?
I can hear you. Slow, but I can hear you.
For the spacity value, it should be less greater than 0.05 for it to be significant, right?
Correct, correct. Null hypothesis says
Okay.
that sparsity is not violated.
Not violated, and the alternatives it is violated.
Yeah. See, for understanding purpose, we only will talk about null
I
hypothesis.
understand. Okay, not an issue. So that means it should be greater than 0.05 for us to go ahead. That's the only thing you have to
Correct,
remember, right?
absolutely correct. It should be more
Okay.
greater than 0.05.
To interpret the next results, further results.
Yeah. If it is
Okay,
greater than
sir, thank you.
0.05, then we need to come into this test of within subject effects table. In this methods, you must see sparsity assumed, because we are assuming sparsity is there. Then only you need to see this value. So this is all about one-way repeated measure ANOVA.
Thank
Now,
you, sir. Thank you.
yeah. Okay. Now let us go for the next topic, which is called as two-way ANOVA. Okay, we discussed one-way ANOVA, one-way repeated measure ANOVA we discussed. In one-way ANOVA, we discussed about post-hoc test also we have discussed. And now we are discussing about two-way ANOVA. Two-way ANOVA is where we have more than one independent variable. The difference between one-way and two-way is in one-way we have only one independent variable. In two-way, we'll be having two independent variables. Remaining all conditions need to be satisfied. Now let us take one example. Yeah, this is two-way ANOVA example. Now, you can see the data. Here we are having three variables: writing ability, teaching methods, and marks. Labels also you can see. Writing ability, teaching method, and marks obtained by student. We want to investigate, we want to do the research and find, is writing ability and teaching method impacting the marks, students' marks. Okay, so here writing ability, if you see the levels, there are three levels are there: poor writing ability, good writing ability, excellent writing ability. Three levels. And methods, they have given training to students in two methods, method A and method B. And this is marks. So you can see the dependent variable is scale. And we have two independent variables. And both are nominal data. Both are nominal data. If you see the values, you can see here, we have first student got good writing ability, teaching method is B, and the marks he or she scored is 20. So here we have total 18 students are there. So we want to investigate, does writing ability and teaching method impact the student marks? So for this purpose, we will do the analysis. The important condition is we have one dependent variable and we have two independent variables. And these two independent variables are nominal data, and a dependent variable is a scale data and normally distributed. Okay? And if you're strictly writing some research, you must even see the homogeneity and so many other things also you must see. But for time being, you only take these important assumptions. The nature of dependent variable, nature of independent variable need to be understood. Now let's start the analysis. Analyze. And in this general linear model, and within this, we need to go for univariate. One-way ANOVA we did from comparative mean. One-way ANOVA we did from comparative mean. Directly we did one-way ANOVA. But when you're talking about repeated measure ANOVA analysis, general linear model, in this repeated measurement. And when you're talking about two-way ANOVA, we must take univariate. Should be taken. Why it is univariate? Because we have only one dependent variable. So let me click this univariate. Now in this, we need to select a dependent variable. Dependent variable is marks obtained by the students. And fixed factor, random factor, covariates. If here both are nominal data, we are making as a fixed factors. In case we have what you call continuous data, scale data, you must keep it as a covariate or you must keep as a random factor. You must not enter in this a fixed factor. But time being, we have two variables here, writing ability and teaching method. Both are nominal variables. So I have entered into fixed factors. Now, here we can go to options. In options, we can select descriptives. Can select homogeneity. If you want to check the homogeneity of data, we can select homogeneity. Okay. And here heteroscedasticity. We'll discuss this in regression analysis. This is a very important statistical assumption for regression analysis. Homoscedasticity. But let me show you in the regression, or we'll see this here only. When you want to check this heteroscedasticity, we must select this method which is called as Bruce-Pagan test. Hello, can you understand what I'm saying?
So can you do this once again? Yes.
What I'm doing is, I think this you understood, right? Till here?
That's the general linear model, which is
Analysis in this general linear model in this univariate. You must select univariate. Now, once I click univariate, now we need to select the dependent variable is scale data. That is, in our case, it is marks obtained. And these two nominal data are taken as fixed factors. Writing ability and teaching method. Writing ability and teaching methods. Now, is it okay till here?
yes, sir.
Yeah. Now select options. In options, we must select descriptives. And here, actually, you need to see one interesting thing here. This is called heteroscedasticity. Heteroscedasticity. Anyone participant have an idea what is heteroscedasticity? Very, very, very important assumption when we do regression. Many people, I think, they did regression analysis many times, but never generally people will not do this homoscedasticity test or heteroscedasticity test. This is a very
variances
important.
are different.
Yes, sir.
Variances are not equal to 0.
No, this is
heteroscedasticity.
Homoscedasticity or heteroscedasticity is different. We are going to talk about the residuals of the dependent variable relation with the independent variables. We are going to discuss about homoscedasticity as a residual. I think you know what is a residual. Residual is nothing but am I confusing you?
No, sir. I think you can explain.
Yeah. Now, when you talk about variance is not equal to 0, the statement is not so simple. The homoscedasticity is a property. Like I was saying earlier, sparsity. Sparsity is a property. It's a nature. The same way, we must even check the data property nature with a method that nature is called as homoscedasticity or heteroscedasticity. What is this homoscedasticity or what is a heteroscedasticity is? We must take the variance of the residual and compare with the independent variables. Then, if they are having uniform, they are having equal distribution, then we call it as a homoscedasticity. You must always see that the data is homoscedasticity. The property should be there for the regression analysis, to perform the regression analysis. There are like 14 to 16 assumptions are there to do regression analysis. In this, I'll be listing in this workshop 3 to 4 important things I'm going to discuss, because if I discuss all other things, it become very confusing, very disturbing. So we'll see, actually, we'll discuss this heteroscedasticity or homoscedasticity in regression analysis only. When I explain you it graphically, I'll again come back to the same screen and I'm going to explain you once again. So for the time being, I'm not doing this heteroscedasticity. Only you remember this heteroscedasticity test we are going to do with the Bruch-Paget test. This is one of the tests. And always you must check for the homogeneity. We discussed about homogeneity, right? Can anyone say what is homogeneity is? Hello. What is the meaning of? It's also property. Homogeneity is also, these are all properties of the data. These are the properties of the data which need to be satisfied. We say, no, for recruitment to happen, the student should have so many marks in at this level. He must get so much marks. He must be so much height and so much weight. These are the properties. If they are satisfied, then only they will be recruited for that particular position. In the same way, if these all assumptions are satisfied, then only you must do the test. It's not that we have some Spss software and we simply keep the variables there and we get the results. You must always check all these assumptions and write systematically. Then only that paper will be qualified for writing for international journals. People are expecting this all tests to be done. So what is homogeneity? Can anyone say? Shall we go ahead? I think we already discussed yesterday also homogeneity. Leibniz test of homogeneity we discussed. Hello? Anyone remember? So Leibniz test? Hello?
Yes, we did discuss, but I think
yeah, we discussed about Leibniz test in two independent sample t-tests. Like we have male and female, their performance marks. What is homogeneity? The variance of male and the variance of female are equal in terms of the marks. Means it is homogeneity. Data is having homogeneity. Variance assumed, equal variance assumed, we said. So that test must be done, because see, when you're conducting competition between male and female, if they're not having equal variance, there is no meaning of doing with a particular test. We must change the test and do. If the variance is equal, we must use one type of test. If the variance is different, we must use another type of test. So homogeneity need to be also discussed. It's also one of the important assumptions for doing this parametric tests. Right. So for time being, we are only going with the descriptives. I will discuss this heteroscedasticity when you discuss linear regression, because there it carries actually a lot of importance. Then this two-way ANOVA. Two-way ANOVA is a bit easier one. Let's go with the descriptive. Only descriptive I am selecting. Continue. And let me click OK. Now you can see here. Between subject factors, numbers it is given. Total 18 members are there. 6 members in poor writing ability, good writing ability 6, and excellent writing ability 6. And we have 2 methods, A method and B method. Descriptives, we can see the combination between writing ability to teaching method. How many marks they got. We can see there is good score for excellent writing ability, with a combination with the teaching method B, their students have 36.67 marks. So it is working better. There's a very poor marks at poor writing ability with a combination with the method A, 26.67. These are least marks which they got. So let us see whether there is a relationship between teaching method to marks. If you see this test of between subject effects, if you see this writing ability column, that is only the significant value. The significant value is 0.033. It is less than 0.05. It means writing ability is having impact on marks. Or you can say there is a significant difference between writing abilities towards marks. Naturally, poor writing skill will get less marks. Excellent writing skill people will definitely get more marks. But coming to teaching methods, the significant value is 0.901, which is more than 0.05. So there is no difference between teaching method A to teaching method B. So teaching method does not have any sort of relation with the marks. Whether they are getting trained by teaching method A or B, that does not make any difference for the students. But writing ability is definitely having an impact because the significant value is 0.033, which is less than 0.05. So we can conclude that yes, teaching ability, writing ability has impact, whereas a teaching method does not have anything to do with the marks. And one interesting thing is we need to understand the interaction between writing ability and teaching marks. This is interaction. Interaction is combination. When poor writing ability with A method, poor writing method with B method, excellent writing method with A method, excellent writing method B method. When you take the interaction is significant. Interaction variable is having significant value, 0.047, which is less than 0.05. Which is less than 0.05. So this is a very important catch for the research. Interaction is also having significant, and writing ability individual has significant. Teaching method does not have it, but interaction of writing and teaching again have it. It means that writing ability is very, very powerful in getting the marks. Because even when you combine with teaching method, also it is showing good result. Right. So interaction variable is nothing but it's like a moderation analysis. When you do in structure equation modeling, we do moderation analysis. In moderation analysis, we'll have interaction variable. We always talk about interaction variable. So that is the same type of property here we have for writing ability into teaching method.
Hello, sir.
Yeah, please.
So can we say here that the teaching method is the moderating variable here?
No, it's not. We cannot say that which is moderating now. Moderating is we can take interaction. We can take the interaction. Anything can be moderating, sir. We can say even writing also can be moderating.
Okay, right. So we have not decided which is moderating, but there is an interaction. That means there is a moderation effect.
Correct. Why? Because it's only multiplication of A and B.
Hello, sir.
Okay.
Yeah, we cannot say which is moderating. Only thing we understand interaction means a property. When you discuss that structure equation modeling, I'll show you. There always we'll create one new variable in moderating that is called interaction variable, which is there, which is not there in the model.
Okay, so understood. Got it. Thank you.
Sir.
Yeah.
Am I audible, sir?
I can hear you.
Sir, you're talking about all those assumptions that you need to make, homogeneity, normality, all those things.
Correct.
If we don't do that and we run the test, is there a way that SPSS will tell that the data is not normal or that way? Or it doesn't just...
When you do, for example, just now we are discussing about Bruch-Pagan test, I said, heteroscedasticity. It is giving the result automatically, no?
Okay. Like, let's say if the data is not normal and I've run the test, will SPSS tell me that the data is not normal?
No, sir. Now, as of this version, what we have, it is not intelligent in navigating us.
Okay.
in guiding a system, the software that events a package, the package is not intelligent as of now to guide us whether to go to the test because you don't have this method satisfy, you not assume this one. You cannot do that. In that way, it's not this, sir, because it is now free. It is not guiding as of.
Okay, okay, sir.
Automatic guidance is not this, sir. We need to take our own decision basing on the test only. As of now, don't know. Maybe intelligent people will do it in near future.
Okay, sir. Okay. Yes, sir.
That is also going to happen, sir. Day by day, we will become more idiots.
Okay, sir. Thank you.
When you give the data, everything. No, I have seen some software. It is writing interpretation also. It is not artificial intelligence software as of now, but they have developed one type of software. But as of now, SPS says no. We need to take a decision.
Okay, okay.
Yeah, because I'm using 25th version only. I've not seen the higher model. Maybe in the higher versions, it may be there. I don't know that because I need to accept my ignorance also.
Okay, sir. Thank you, sir.
Yeah, let me go ahead. Now, this is all about two-way ANOVA. And the important things we have discussed is we are seeing interaction, we are seeing individual variable impact as well as interaction variable also we are seeing. Writing ability into teaching method is an interaction variable. So we conclude that writing ability is significant, teaching method is not significant, and interaction is having significant impact. Now, let us go to the next method. Anyone have any doubt? They can ask at the moment.
Hello.
Now we'll go for the next topic, which is called MANOVA. MANOVA is nothing but like ANOVA only. Only thing is we are going to have two dependent variables here. Multivariate ANOVA. This is MANOVA. So where we have more than two, we'll be having more than one. There's a two dependent variable. We call it as a MANOVA. Okay. Let me show a small PPT also for that. MANOVA, which is multivariate analysis of variance, is a statistical technique used to analyze the difference between the means of two or more groups on multiple dependent variables simultaneously. Now we have a lot of assumptions are there. Now here we are going to discuss about normality. These are all the 5 assumptions. Actually, there is one more assumption is also there. I've intentionally not showing you because a lot of discussion need to be done on that. Actually. But we can see these are the primary. These are the very basic one. The first assumption is independence. Each participant should take part in the research only once, and their involvement should not influence the participation of the others. It means don't combine and take them in one place. You take separately, and each respondent, each row is a respondent. They're not influencing the other participants. Normality. We need to do both normalities. Univariate normality test must be done, and multivariate normality of distribution should be done. Earlier, we discussed only univariate. Kolmogorov, Smirnov, and Shapiro-Wilks test is only for univariate. But in this MANOVA, we need to do 2 tests. One is univariate, the other one is multivariate normality. If multivariate normality is there, then only we need to go for further analysis. And third, we need to check multicollinearity. It's a characteristic by high correlation between dependent variables. Okay, so we need to select, we must discuss about multicollinearity of the data. Next, we need to see cell size. Cell size, actually, this is not important because generally we get this cell size. We'll definitely get more than the dependent variables. Each cell size should be more than number of dependent variables. For example, we are having 2 dependent variables. The cell size should be more than 2. If you remember, I was showing cross tables. In that, I was showing expected count cells. I was showing in the same way. When you see a table, you are going to get cells where the count should be more than 2. If you have dependent variables, 2. If you have 3 dependent variables, you must have count more than 3. And the 5th one is homogeneity of variance. This is not homogeneity of variance. Actually, this is homogeneity of covariance matrices. We'll be discussing homogeneity of covariances we are going to discuss. We are going to discuss two things: homogeneity of variance, covariance matrices. Similar to the homogeneity of variance assumption in ANOVA, there should be homogeneity in the variance covariance matrices across groups. So these are the 5 important assumptions that need to be fulfilled. Then only we are going to do the analysis for MANOVA. Anyone have a doubt? You can ask at the moment. I'll show each assumption separately. First assumption, nothing to do. It's only just a data collection part. We'll start from the second normality. Second normality, that is second point. Normality, I'm going to show you. Multi-collinearity test I'm going to do. And I'm going to do this homogeneity of covariance matrices also I'm going to show you. Anyone have a doubt? They can ask at the moment.
Sir,
Yeah.
in the if you are not given the if we have not given the Excel sheet, and if we are given only interpretation data, so how can we know that this is a dependent and independent variable?
Just a minute, I'll show you example, madam. In this example, madam, can you identify which is dependent, which is independent? Yes, we can identify marks are dependent and these two are independent, right?
No, not in this, sir. In this interpretation, not if it. I'm saying if it is not given this Excel sheet, this data, only interpretation is given, then how can we find it out?
Read it, if you give interpretation, it is obviously they need to explain, right? In interpretation, basically, first they must explain what analysis they are doing, which is impacting which, what is the purpose they are doing, what is the null hypothesis. Everything need to be explained, right? When you read it, definitely you'll understand which is independent, which is dependent.
Yeah, that is okay. I was just thinking like, yeah, now you have told that they should give it actually.
Definitely should be given. It's like a storytelling, no? Interpretation, nothing but explanation.
Yes, sir.
Yeah, if you want to see a story without explaining anything about the characteristics, how can we understand the story?
Yes, sir. Correct.
Characteristics is nothing but variables, they must explain the variables.
Yes,
relationship
sir.
Variables, like whether their characters are brothers relationship or what are the relationship. They will explain the relationship. Then only we'll understand, okay, how the story is going on.
Okay, sir.
If someone is giving without any sort of thing, it means they are not actually writing the interpretation what is required, only just half-baked type of interpretation.
Okay, I got it. Yes.
Yeah. Sorry, Andy. I want to discuss and elaborate. I'm saying so many things. Don't think otherwise.
Yeah, sir. Okay, thank you.
So let us see this MANOVA. Important thing is, before discussing this MANOVA, I said we are going to discuss these things, important things like normality. Uninormality we'll discuss, multivariate normality. And we'll discuss about multicollinearity. And we'll discuss about homogeneity of variance covariance matrices. Earlier we discussed about homogeneity of variance only we discussed, but we are going to now discuss about homogeneity of variance covariance matrices also we are going to discuss. Now let me take the example. MANOVA. Let's create that file. Yeah. You can see this example where we have 3 independent variables. Again, marks we are taking because this is easy to understand. That's why we took this one. English marks, mathematics marks, and science marks. And teaching method. We have one independent variable. There are 3 dependent variables. 3 dependent variables: English marks, mathematics marks, and science marks. And training method is only one independent variable. So you can see here also. So in this MANOVA, we'll be taking 3 dependent variables, 1 independent variables. Objective, we want to see is a training method impacting marks, English marks separately, mathematics marks, and science marks. So this is what we are going to discuss. Null hypothesis can be made. There is no significant difference between methods towards English marks. There is no significant difference between training methods towards mathematics marks. There is no significant difference between training methods to science marks. You can see methods are three type of methods: A method, B method, and C method. And dependent variables are scale data. That's the primary assumption which we have made, that dependent variables will be scale data, independent variables will be nominal data. There is a basic rule which I already said before starting one way and the same thing we are taking. Only difference is here we are going to have more than one dependent variable. Now, the first thing we are going to see is we are going to see univariate as well as multivariate normality. Shall we discuss, or if you think not required, we can skip this also.
Sir, please discuss, sir. Thank you.
Shall we discuss?
Yes, sir, please.
Yeah. Univariate already we have discussed. I'll just show you once again. Analyze descriptive statistics. In this explore we have taken. In this, we can select each individually: English, maths, and science. And you want to see in terms of training methods, you can select label cases by. Okay, we have selected English, maths, and science. Three data we want to see. And the training method wise, if you want to see, you can select this one. Plots, normality plot with a test, and normality. Click continue. Click OK.
Excuse me, sir.
Shall I go ahead? Yeah.
Once again, please, sir. I want to process. Hello.
Yeah, I can hear you.
Sir, please, can you repeat the process once again?
Yeah, I'll show you. Analyze descriptive statistics. Explore. When you click explore, we get this table. In this table, select all the dependent variables to check the normality. You have to select all the three. And the training method must be selected as labels cases by. Labels, training methods. And in plot, select plot. In plot, select normality plot with the test and histogram. Click continue. Shall I go ahead?
Yes, sir.
Yeah. Click OK. Now here, we are going to get the test here. Now you can see here, the test of normality. The total sample we are having is 96 actually. 96. So 96 is less than 200. So here we can select a Shapiro-Wilks test. Shapiro-Wilks test. Now here English marks, it is more than 0.05. You can say there is normality. Univariate normality is there for English. For mathematics marks, we don't have normality. We don't have normality. And for science marks, we have normality. For science marks, normality is there. For English marks, normality is there. But for mathematics marks, normality is not there. So the null hypothesis, actually assumption is data is normally distributed. There's an assumption. If the significant value is less than 0.05, we reject it. If it is more than 0.05, we accept it. If it is 0.05 and more than 0.05, we accept it. In these cases, this is having normality. English marks, normality is there. Mathematics marks, there is no normality. But science marks, normality is there. Right. Let us see the diagram also. English marks, double click here and take this diagram and close it. We get this normality. And for mathematics, these are mathematics. Double click this icon, distribution curve, close this and close this. Yeah, normality is not, because the bell structure is not complete here. And coming to, yeah, this is perfect. Science marks perfectly, we have normality. Yeah, this is not. So univariate normality, I have shown you univariate normality. Is it okay?
Yes, sir.
Yeah. Now let us do multivariate normality. For doing multivariate normality, we must do regression analysis. We cannot do in this MANOVA. To check the property of multivariate normality, we must do regression analysis. I'll just show you how to do that regression analysis for multivariate.
Hello.
Yeah.
So sorry, there was a question. Now you saw that the marks, English marks was just about normal, and maths mark were not at all normal. So now what to do with these variables now? Or have to just keep it that they are not normal and we can't use any test?
Yeah. If an assumption is not satisfied, now English marks is qualified. So we cannot say just or above. It is qualified. Just take it as qualified. That's it. We are going to accept it now. But mathematics marks are not normal. We need to exclude it.
So we have to just exclude that variable because it is not normal, perfect. And we cannot use
this
according
test. To assumption.
Yeah.
According to statistical books, we need to exclude
but still if we
mathematics.
No, but we still go ahead with that maths marks also. It is okay. The results will not be correct, right?
For discussion purpose, I am taking it ahead. But if you're writing research, you need to exclude mathematics. Okay, we need to exclude mathematics marks because it is not having univariate normality.
Oh,
okay, so, sir, in short, there is no way out. We need to just exclude the variable.
See, anything you do to control the normality is actually controlling the data. When you control the data, results will be
Okay, sir. Okay, sir.
That's only the problem. We control the data. It means we are controlling the result somewhere.
Correct, sir. Correct. It is biased. Correct.
Biased means automatically we'll have the results which we get. We may not accept it. We may not look the correct resemblance of the population. Right. Now, let us do multivariate. When you are doing multivariate normality, we cannot do in MANOVA. We must do in regression analysis. So now I'm doing regression analysis. Even if we have not discussed the topic, I'll directly do it here just to show you only about this multivariate normality. Analyze in that regression. In regression, we are going for linear. So, can I go ahead?
Yes, sir.
Analyze regression linear. Why I'm going to linear regression? Because I want to show is there multivariate normality for the 3 dependent variables. Now here something tricky you must do. You select a training method as dependent and this 3 as independent. Okay. You select there's a training method as a dependent for time being only to show multivariate normality for these three combined. So you must take, when you say multivariate, even though they are dependent in MANOVA, here you need to treat them as independent. Now click save button. Here click save button. Click save button. In this save button, you must select Mahalanobis distance, because there are different methods to do multivariate. In SPSS, we are doing with Mahalanobis distance method. We are doing with the help of Mahalanobis distance method. Click Mahalanobis. I have selected this button, save. In this, we need to select the distance Mahalanobis, because to select do this multivariate normality, you must use Mahalanobis distance. Click continue and click OK. That's it. I'm not doing any more setting. Directly, my objective is to see whether multi-normality is there or not.
रुखसार बेटा मैं वो भेजी ना तुम्हें देखे.
Click OK. Now here, you need to come to residual statistics and see Mahalanobis distance value. Mahalanobis distance value. This is important. Directly come to the table, which is called residual statistics. In this residual statistics, you need to see Mahalanobis distance and note this value. This value is 14.404. This is a value which we need to write on the research. The Mahalanobis distance maximum value, you can see the maximum value. Maximum value is 14.404. 14.404. Now, once you get this value, you need to select a chi-square table. There's one table we'll be having, just a moment. In MANOVA. Critical values for Mahalanobis. This you can get in internet. This is chi-square value. Generally in statistical books, at the end they'll give you the chi-square values. They'll give you the total of critical chi-square values. Generally, you'll find this table in statistical books at the end. You can take that help, or internet also you can available these values. In this, you must see p-value for 0.001. For this, how many dependent variables we have in MANOVA? 3, right? So degree of freedom 3 must be seen. For degree of freedom 3, you must see this value. For p-value 0.001. What is the value we got? 16.27. 16.27. So the Mahalanobis distance which we got there, maximum one, is 14.404. That value must be less than this critical value. That value must be less than this value. This value is 16.27. But how much value we got there? Maximum Mahalanobis distance value 14.404. If that value is less than this value, then we say multivariate normality is existing between the dependent variables. Then only we can say multivariate normality is existing between the dependent variables. I think, am I clear? How to check multivariate normality? You need to go to regression analysis, do all the settings. In the output, you must find in residual statistics, you must select this maximum. In this Mahalanobis distance value, you must see. And in the book value, we call this a book value, statistical book value. For p-value 0.001, degree of freedom 3. Why? Because the dependent variables are 3. If your dependent variables are 2, then you must see for this value. But in our case, we have 3. It is 16.27. So that maximum Mahalanobis value, if it is less than this value, that is of 14.404. Now it is 16.27. So 14.404 is less than 16.27. So we conclude multivariate normality is existing between the three dependent variables. Henceforth, we can go ahead with the analysis.
One question, why
Right.
is that you are using p-value 0.001?
Yeah, it's a standard one we use generally. That's a standard notation.
Because normally we use p-value of 0.05, right?
Yeah, you see, if it's up to you, we can use even 0.05 we can use, but generally standardly they'll use 0.001 only they'll use. If we use, for example, if we use p-value 0.05, the value is 7.82 only.
No, that's why I'm asking, just asking.
That's why, that is why some privilege type you think, because I have also noted this point. Some privilege, many research they are using, even though they are using alpha is equal to 0.05, when it comes to critical value, they are using p-value 0.001.
So we can consider it as a thumb rule, sir.
Yeah.
Can we consider it as a thumb rule?
Can we consider it as?
Thumb rule.
Yeah, we can take as thumb because many research have used that way. That is the way I'm giving, so that we can come to an assumption saying that multivariate is there. If not, no, many cases multivariate will not be there at all. Many cases. So we cannot do MANOVA at all in that cases. Okay. So if you want to use p-value, p is equal to 0.05, you can go ahead. But only thing is, we are going to stop the analysis at this point.
Sir, but anyways, one sample has already failed in the normality test.
No, it's a discussion purpose I'm showing. Discussion
Yes.
purpose I'm showing. That is all tentative data with prepared data. That is.
Okay, sir. Okay, sir.
Tentative data. That's what I said. No, if univariate you are saying mathematics marks are not there, you remove it automatically there and do with only two variables. Only do two variables and again check the value. If it is also here we have multivariate, then you can go ahead in the analysis. Right. And so this is all about univariate and multivariate. Now next we will be discussing about multicollinearity. I think many people knows what is this multicollinearity. Multicollinearity must not be there between the dependent variables. If there's a high correlation, then we need to remove the variables. So we need to check the same multicollinearity also. We can use a regression analysis once again. Same regression analysis, what we are doing, we do once again. Shall we go ahead with multicollinearity?
Yes, sir. Yes, sir.
Yeah. Analyze. Same regression. Linear. Now in this, we can go to options. Not options, statistics. In statistics, collinearity diagnostics. Collinearity diagnostics. And click continue. I'll just show once again. We are selecting statistics. Same regression analysis. We must select statistics. In this collinearity diagnostics.
One question, sir. Here, shouldn't the marks be dependent variable in each one?
No. Here we are trying to understand the relationship between these three. So we cannot keep in regression more than one dependent, right?
Yes.
That's the reason we are taking. That's why I said MANOVA. In MANOVA concept, they are independent, but we want to check the multicollinearity between the dependent only. So in this case, we are typically considering because in SPSS they are given regression only those possibility. That possibility.
Okay. Thank you.
So and many people will do regression, so it is easy to understand. That's why I came to regression for multicollinearity. Here, collinearity diagnostics. Collinearity diagnostics. Click continue and click OK. Now here we must see VIF value. In collinearity, just see coefficient. Don't discuss anything about these values. We're not interested in all these values. We are only discussion about this tolerance and VIF. VIF. This VIF must be less than 5. Less than 5. Variance inflated factor. Just actually one PPT also. Just a prepare one. Yeah. So multicollinearity is a phenomena in regression analysis where two or more independent variables in a multiple regression model are highly correlated. Okay, you can see this value. Variance inflation factor, we are going to see. If it is equal to 1, there is no multicollinearity at all. There is no problem at all. If this value is between 1 to 5, we call it as a moderate multicollinearity. 1 to 5. That's why we say it should be below 5. If it is more than 5 or equal to 5, high collinearity. We cannot accept this value. And if it is more than 10, very high multicollinearity. So the value, the best way we can accept is this value. Moderate multicollinearity. We cannot expect this value at all because this is only an imaginary figure. VIF never can be 1. There is no multicollinearity at all. But here multicollinearity can be to this level. That is, it can be between 1 to 5. So in our case, the VIF value is 1.205 for English, for maths 1.27, for science 1.127. So multicollinearity problem is not there. It's only moderate multicollinearity between the subjects. So this is how we have discussed the multicollinearity issue. Is it okay?
Yes,
Am I
sir.
confusing you or I'm teaching you properly? Hello?
You are good, sir.
Yeah, able to understand? I'm not confusing anyone, right?
No.
Because see, some way we must discuss. I can also make it very smooth, run like a cakewalk or moonwalk, whatever it may be, and I can make you beautiful figures and I can show you everything. But genuinely, many people are doing research. They need to know it, even though they find it tough. But this is all what need to be actually done, because nowadays many
Hello,
people are
sir.
getting suffered to write articles for international journals.
Hello. Hello.
Yeah.
So there's a question there. If you guys could go back to the results of the multicollinearity test, please.
Yeah.
Sir, if there is multicollinearity, which variable should be dropped? Looking at the correlation values or looking at the significant values?
No. Don't bother about these significant values, because this is not what we're expecting. We're only talking about VIF values of these 3 variables: English, maths, and science.
I understand.
Here,
I understand, sir. That is not the question.
If VIF, for example, for mathematics is 5.7, for example,
Okay.
it means English is not having, is having a problem, is having multicollinearity. Then when you see the correlation between the values, then you'll understand which is the variable which you can drop.
Okay. So with the high VIF value should be dropped. Hello.
Yeah, that's correct.
High VIF value should be dropped. Okay, thank you, sir.
Correct. That's correct. Now let us go for the next topic, which is called as homogeneity of variance covariance matrices. Okay, this I'll discuss when we do in MANOVA test only. When I do MANOVA test, we will come to this homogeneity of variance covariance matrices. Let me start a MANOVA analysis. Yeah, let me do MANOVA analysis. I'm removing this all Mahalanobis values. Clear? Now save it. Analyze general linear model in this multivariate. In this multivariate. Analyze general linear model multivariate. Now, the dependent variables are English, maths, and science. And fixed factor independent variable is training method. Training method. Right. Is it okay? Can I go ahead?
So can you do it again?
Yeah. Analyze the general linear model in this multivariate.
Yes, sir.
Yeah. Now, in this, we have three dependent variables: English, maths, and science. Training method is fixed factor. Training method fixed factor. Right. Let me go to options. In options, we can select a descriptive statistics, homogeneity test, and click continue. Click continue. These are options. And in plots, select plots. Select plots. You can select training methods as horizontal axis. Click add and click continue. Click continue. I've not did any more settings. I have did a very small settings like options. I've selected descriptive statistics and homogeneity test. Significant value 0.05. And in plots, I've selected training methods. Here you can see the training methods. Already I did the analysis and I click continue. Now let me click OK. Can I click OK?
Sir, in options, what we have to select?
Yeah, only two options I've selected: descriptive statistics and homogeneity test.
Okay.
Homogeneity test. Only two options I've selected. Click continue and click OK. Can I go ahead?
Yes, sir.
Now here we can see between subject factors, we have A method 32 members, B method 32 members, C method 32 members. So each cell we have more than 3 because 3 dependent variables. More than 3 we have. And the descriptives, you can see these are descriptive values. The combination of marks and method. Combinations of marks and methods. English, maths, and science. You can see all the values in descriptives. Now here, box test of equality of covariance matrices. This is what the homogeneity we are talking. Here I will just shown you homogeneity of variance covariance matrices. This assumption, to understand this assumption, we must see this box test of equality of covariance matrices. The significant value must be more than 0.05. Significant value must be more than 0.05. In case if it is less than 0.05, we will stop the process here only. We cannot go ahead. Okay. So the fifth condition, homogeneity of variance covariance matrices is tested with the help of box test of equality of variance matrices. Sorry, equality of covariance matrices. The significant value must be greater than 0.05. If it is less than 0.05, we cannot accept it. We are going to say homogeneity of covariance is violated. Is it okay?
This violation principle, can you explain it again?
Yeah, you can see box test of equality of covariance matrices. In this test, you see the significant value. We got significant value as 0.079, right?
Yes, sir.
It is more than 0.05. So we can conclude that homogeneity of variance covariance matrices is accepted. Means we are not violating the assumption. We are able to accept the assumption. We are able to fulfill the assumption.
Okay, sir.
In case, I'm saying in case, if it is less than 0.05, we are going to stop the analysis at the moment. We cannot go ahead. Is it okay?
So we cannot go ahead means what?
Stop it. So there's no meaning of seeing the differences.
Okay.
You say there is no difference between three people. What is the fun of seeing whether there is a significant difference? So
Yes,
we'll stop the analysis here. Means we'll say that further. We'll write it that the homogeneity of variance covariance matrices is violated. Henceforth, further analysis is not done.
Santosh sir, 6 ನಿಮಿಷ ಮಾಡಿದಾರಂತೆ PhD.
And after that, is it okay?
Yes, sir.
Hello?
Yes, sir.
Now we are going further to see whether there is any difference between the methods towards the marks. Okay, we can see this Pillai trace, Wilks lambda, Hotelling trace, and Roy's largest. You can see this value. These values must be less than 0.05. Then only there is a significant difference between teaching methods towards the subjects. Towards the subject. You can see Pillai trace. First, you must see the Pillai trace. There's a lot of explanation is there, but it takes a lot of time to explain why each method need to be selected. But in simple way, you must see this must be less than 0.05. And after that, we need to see between we are not seeing. Yeah. Now here we conclude. We are saying that there is a significant difference between training methods towards the subjects. And if you see for subject wise, training method wise, for this is for English. See, training method A and B are having A and C is having very less, but B method for English there is a very high value is there. And coming to training method wise, mathematics wise, there's a difference. Even in this case also, B method is working very well. C method is not working. Now coming to science, there is a difference is there. Again, in this case also, B is having highest marks, whereas A and B, C are not having highest marks. So henceforth, we can conclude that there is a significant difference between training methods towards the subject marks. Is it okay?
Hello.
Yeah.
Hello, sir. Is there any post hoc here?
Yeah, we will have post hoc.
Post hoc test.
Yeah, further discussion takes a lot of time. Yeah, there is a discussion. Further, again, we need to see between English to maths to science.
Got it, sir. Got it. Thank you.
Now, this is all about MANOVA test. We'll close this MANOVA test. Now we'll discuss about correlation. Yeah, I think everyone knows correlation. Correlation is a relationship between scale variables, right? Now we have two types of correlations, Pearson correlation and Spearman correlation. When we must do Pearson correlation and when we need to do Spearman test.
Pearson, when we have
Yeah, please go ahead. Please. Please go ahead.
then are you able to hear me?
I can hear you.
Yeah. Pearson, when we have scale data or maybe ratio scale, and Spearman's when we have nominal or ordinal.
Nominal we don't do actually, but ordinal data. Nominal we must not do. We must do chi-square values.
Ordinal, I mean, ordinal, sorry.
Only ordinal. For nominal, we don't do correlation. We do cross tables and see. There are different conditions are there, but we'll talk in a safer way, in a simple way. Right. That's fantastic. What you said is absolutely correct. When you want to see the correlation between two variables, if it is scale data, we need to use here one. Just I'll show you. Analyze correlation bivariate. In this, we have Pearson. So we are using Pearson because the variables are scale data. I want to see the relationship between correlation between job experience and education. Job experience and education. Job experience and education. And Pearson. Click OK. Now here we are going to see the correlation value. Correlation, the value which you are seeing, this is correlation. We have positive and a negative. This correlation will be ranging between -1 to +1. Okay. Zero correlation means there is no correlation between the variables. If it is more than 0.7, we called high correlation. Okay. So minus and plus is only direction. We must first see the significant value. Here in this case, the significant value is 0.033, which is less than 0.05. We can say there is a significant correlation between job experience and years of education. Job experience and years of education. So this is all about the Pearson correlation. Anything we want to discuss at this moment, we can say. In case, if the data is ordinal data, then we are going to go to same navigation and take Spearman correlation. That's it. All interpretation, everything is pretty much same. We are going to do the same type of interpretation in this case also. Right? Any discussion, anyone want to ask any doubt, we can ask at this moment. Shall we go ahead? Hello? Hello?
Yes, sir.
Yeah, shall we go ahead?
Yes, sir, sure.
Right. Now we need to discuss from here onwards the linear regression and logistic regression. In linear regression, we'll discuss all the assumptions of regression, and we'll do linear regression. We'll discuss all the aspects of linear regression. After that, we are going to discuss about multi-nominal logistic regression. So these are the topics which we need to discuss further. So I want a 5 minutes break. Can I take?
Yes, sir. Even we need a break.
Yes, sir,
Yes.
please.
So it's now 6:05. By 6:10, again we'll join.
Thank you. Thank you so much, sir.
Yeah, hello. Hello.
Yes, sir.
Can we go ahead?
Yes, sir, please.
We'll discuss now about linear regression. Just a minute. Yeah. So regression is an impact study. So everyone knows that regression is impact study where we have one dependent variable and multiple independent variables will be there. So this, if you want to study the regression analysis impact study, then we need to do regression analysis. And these are the 6 assumptions which need to be satisfied before we do regression analysis. Let me show the example first and we will discuss that analysis assumptions. Now here, in this regression analysis, sales is a dependent variable and we have 2 independent variables. One is experience, other one is education. And we want to see what is the impact of experience and education on sales. If you have only one independent variable, it is called a simple linear regression. In case if you have more than one independent variable, it is called multiple linear regression analysis. So here we have more than one independent variable, so we are calling it as multiple linear regression. Right. Now, we are taking the first assumption, linear. Linear in the sense, there is a straight relationship between independent variables and dependent variables. Before we start linear regression, we need to satisfy these 6 assumptions. The first one is linearity. The relationship between independent and dependent variable is linear. This can be checked by the simple plotting the data and looking for straight line relationship. The next important one is homoscedasticity. This is what I was discussing earlier also. Heteroscedasticity and homoscedasticity. This assumption must be satisfied. The variance of residuals is constant across all values of the independent variables. This I'll show you the analysis, how to do and how to check this homoscedasticity. Third important is a normality. We need to check both normalities. Univariate normality as well as multivariate normality need to be discussed here again. And the fourth one is outliers need to be identified. There are no outliers in the data. Data must not have any outliers. Fifth assumption, autocorrelation. Residuals are independent of each other. This can be checked by using Durbin-Watson test. Autocorrelation problem must not be there. And the sixth one is multicollinearity. Earlier we discussed this one using VIF. Multicollinearity. So all these 6 assumptions we are going to see one after another. The first one is simple. It's a linear assumption which you're not going to need to do. It's a linear regression. So let us start with homoscedasticity. Before doing this homoscedasticity assumption, let us do the analysis. And within the analysis, we are going to discuss all these assumptions one after another. Is it okay? Hello?
Okay, sir.
Yeah. Any doubts, are you can ask any. Just I'm starting the analysis and I'll show you how to check this all assumptions in linear regression. Right. Now we'll go to analyze. In analyze regression, within regression, we are going to go for linear. Analyze regression, linear. So click on this linear regression. Now here, dependent variable is sales. Select sales as a dependent variable. And we have 2 independent variables, years and years of experience and years of education. Right. Now, shall I go ahead? Further settings. one important point before we go forward. In linear regression, always a dependent variable must be scale only. It cannot be ordinal or nominal. If it is ordinal or nominal, we must do logistic regression. That's a different type of analysis must be done. So linear regression, we are doing under the assumption only that the dependent variable is scale data. In case the dependent variable is ordinal or nominal, then we must use logistic regression, which I'm going to discuss after this. Now we have taken dependent variable and two independent variables. In statistics, I'm selecting the button statistics. Click this value, which is called descriptives and collinearity. Select this collinearity diagnostics. Model fit is already there by default. Estimations will be by default. The extra, what I'm selecting is a descriptives, and we are selecting collinearity diagnostics. If you want to see multi-collinearity, then you need to select this collinearity diagnostics. And select this Durbin-Watson. Durbin-Watson. This is used for auto-correlation. Durbin-Watson is used for auto-correlation assumption. And case-wise diagnostic, we are going to use for outliers. To check where we have outliers, we are going to select this button. Standard deviation, which is more than 3, will be taken as a outliers in this case. Okay. So these settings we have did in statistics. Descriptives, collinearity diagnostic, Durbin-Watson, case-wise diagnostic. In this outliers with the 3. Continue. And next for plots. When you select the plots, this is used for homoscedasticity. For homoscedasticity, we will be using this plots. And here, please carefully see what I'm doing. Select the first one, that is Z predictors. Select it as X. This Z predictor should be selected as X. Z residual should be selected as Y. Z residual should be selected as Y. This is important. You must not forget this setting. Z predictor should be selected as X, and Z predictor, residual should be selected as Y. And here select histogram and normality plots. Normality plots. Is it okay? Hello?
Yes, sir.
Yeah. Is it okay? You must see this carefully. In X, you must keep Z predictor, and Y, you must keep Z residual. And select histogram and normal plot, normal probability plot. Click continue. And in save, click this button save. Select Mahalanobis. Select Mahalanobis. For multivariate normality. Just now we discussed about multivariate normality. In that we discussed about this Mahalanobis. Select only Mahalanobis and click continue. And in options, we don't need to select anything. And now click OK. Now after selecting this linear, dependent variables are sales. Independent variables are job experience and education. In statistics, I have selected descriptives, linear, collinear diagnostics. Durbin-Watson we have selected. Case-wise diagnostic we have selected. Click continue. And plots, I've already said you must select a Z predictor as X, Z residual as Y, histogram, normality plots. And after that, in save, only select Mahalanobis and click continue. And now click OK. Should I go ahead?
Yes, sir.
Yeah. Now, once you select, you'll be getting regression, descriptive statistics. Here you can see the mean values, standard deviation, and number of samples. 110 is the sample. Correlation, you can see what is the correlation between the variables. Okay, we can have correlation between sales and experience, but you can see the correlation between job experience and education is not very high. It is 0.203. It is moderately, we are having the correlation. So no need to get worried about that. Now coming to model summary. Now R square, this is very important. This R square is a variance of independent variables explained on the dependent variable is 0.975. 0.975. This value must be always greater than 0.7, but there is no standard rule that it must be more than 0.7. Better, more the value explained, better the value, better the analysis. Yeah, in this case, we got R square value 0.97 is very high actually. Generally in real-time data, if you have, you will not get such a high data. So R square is 0.975. Can anyone explain what actually this is mean? R square value explains.
It explains the percentage percentage variance is explained by the independent variables.
On the dependent variable.
Yes.
On the dependent variable. Now, in the same table, you will be seeing the Durbin-Watson value. You can see this Durbin-Watson value. This value must be between 1.5 to 2.5. This value, Durbin-Watson, must lie between 1.5 to 2.5. Then we say there is no autocorrelation problem. If it is less than 1.5 or more than 2.5, then autocorrelation problem is there between the independent variables. I just show you a PPT for that. Just a moment. Durbin-Watson autocorrelation. You can see this one. This is about autocorrelation. Durbin-Watson test is specifically designed to detect autocorrelation in these residuals. Autocorrelation means that residuals at one observation are correlated with the residuals at nearby observations, indicating a pattern in the errors that the model has not captured. Okay, if you understand, it's good. If not, you just see that this Durbin-Watson value must be between 1.5 to 2.5. If it is between 1.5 to 2.5, then there is no autocorrelation issue in the data. So this is one of the important assumptions of autocorrelation that we need to understand. Here you can see the autocorrelation. The Durbin-Watson value we got is 2.139. So we don't have autocorrelation problem in the data. If it is less than 1.5 or more than 2.5, then autocorrelation problem is we are violating one of the assumptions of the regression analysis. Next is ANOVA table. In this ANOVA table, the significant value must be less than 0.05. Must be less than 0.05. In case if it is more than 0.05, then we are not able to explain the model. It means the independent variables are not able to predict the dependent variable. The independent variables are not able to predict the dependent variable. So significant value must be less than 0.05. In this case, you can see significant value is how much? 0.000, which is less than 0.05. So we can say that yes, independent variables are able to explain the or predict the dependent variable. Is it okay? Hello? Hello?
Yes, sir.
Yeah, any one participant can keep their mic on and they can prompt so that I'll have, because it's like a blind man going on a road.
Sure, sir.
Anyone, any one or two people can keep their mic on continuously and prompt so that I'll have that satisfaction. Yeah, someone is at least following. I know many people keep that on and they'll do their own work. And pretty much they are giving recorded videos also, no? So no one has the pain of listening, sitting for so many hours and listen. Right. Now let us see
like
this. Yeah, many people. I know the psychology, madam. The coefficient values. So in this coefficient values, now once we see this, I know what if this value is less than 0.05, then only we need to see this coefficient value. In case if the significant value is more than 0.05, then there is no meaning in discussing the coefficient values, right? So in this coefficient values, now we are going to see whether job experience have significant impact on sales. We need to see this significant value. And we make a null hypothesis. There is no significant impact of job experience on sales. Significant value is 0.00. If it is less than 0.05, we reject the null hypothesis and conclude that there is a significant impact of job experience on sales. Next, job education, years of education on sales. This is also less than 0.05. It means there is a significant impact of education on sales. Is it okay? Hello?
Yes, sir.
Yeah. Now, important thing, we need to understand what is unstandardized coefficient and standardized coefficients. Can anyone say what is unstandardized coefficient and what is standardized coefficient, and which one we need to interpret?
Standardized.
What is unstandardized coefficients are? How can we interpret this value? 1868.330 is unstandardized coefficient for job experience. Hello. Hello.
Yes, sir.
Yeah. Now, what is the difference between unstandardized and standardized coefficients?
Don't know, sir.
Yeah. See, unstandardized coefficient means you need to understand job experience and education. These are two independent variables having different scales, right? So job experience, if increased by one unit, the sales will increase by 1,868.330 units. 330 units. So this is the interpretation of unstandardized. And education is also, in this case, it is years. So if 1 unit increase in education, then the sales will increase by 598.220 units of sales. So in this two, which is actually impacting high?
Job experience.
Job experience.
Correct. See, here you can easily say why, because both are experiences, both are in years, you can easily say, right? But in case I have an example, we want to discuss the factors impacting marks. I'll take 3 factors: attendance, IQ level, and hours of study. So 3 independent variables are the number of hours of study is per day, how many hours they are studying, 5 hours, 6 hours, 7 hours in that. IQ is measured from 1 to 10. And attendance, number of days the candidate has attended the college. So 3 variables are there. When you take 3 variables, you want to see impact on marks. Since these 3 variables are different, we cannot see unstandardized coefficient. Why? Because 1 unit is in hours, hours of study is 9 hours, IQ is in a index of 1 to 10, and whereas the attendance is in days. So in that case, we cannot see by unstandardized coefficient, we cannot say which is impacting more and which is impacting less. For that case, you must see standardized coefficient beta value. This value must be seen. right? When you see this one, it means all the three independent variables which are in different units of measurement are now standardized. Now, by seeing this, we can understand which is impacting more and which is impacting less. So when you want to compare between independent variables, you see standardized coefficient value. When you want to interpret independently, separately, then you see unstandardized coefficient value. For regression, we have an equation y is equal to a plus, okay, a plus b1 x1 plus b2 x2. Now, how are you going to write the equation in this case? Sales is equal to minus 8,288.014 plus 1,868.330 into experience plus 598.220 into education. So this is called as a regression equation. So in regression equation, we are writing regression equation. When writing regression equation, we are going to write this unstandardized coefficient values. Then what standardized coefficient value, beta value, we are going to do for comparing which is impacting more and which is impacting less. Am I able to explain properly? You understood?
Yes, sir.
Right. Any doubts are there here?
So, which is to be considered, sir? Standardized coefficient or unstandardized?
That's what I'm saying, madam. When you are saying what is the impact of experience on sales, then you must see unstandardized coefficient.
Okay.
When you want to compare among experience and education, which is impacting more, then see standardized coefficients.
Okay, sir.
Because standardized means when you have independent variables with a different units of measurement, you need to standardize them, then only compare which is impacting more and which is impacting less.
Fine.
Right. And here, if anyone can help me, I'll be very happy. What is this value called as? Minus 8288014. What is value indicates? So how can I understand this value? I know that is constant value, which is intercept value. How can we explain that value? I said about years of experience as 1,868. I have explained if 1 unit increase in experience, then sales will increase by 1,868.330 units of sales. But how can you explain this constant? Yes.
If both are 0, then the constant is negative.
It means if a candidate, you recruit a candidate who is having 0 experience and 0 education, then the sales will be negative. And that is a value. 8,288.014 will be the loss for the company. Right? So this is what you must understand. In case if this constant interpret is not significant, then you write it as a homework, you search internet and see how you are going to interpret if the significant value is not, if this value is not significant, how you are going to interpret the results. You please, it's like a homework for you. You please do the homework and write for yourself. So it must be easy. And one more thing, is it should be significant or not significant? Is it mandated that this also should be significant? We understand variables must be significant, then only we say there is impact. But intercept this value, you do small homework and learn for yourself. But we explained all these values, we have explained you clearly. Now coming to assumptions. Among the assumptions, we have seen...
So one small doubt, sir.
Yeah.
Now in the output, what you showed, here unstandardized beta and unstandardized and standardized coefficient. So yes. Can we say that this like years of job experience, years of education, both are measured in terms of unit of measurement of these two independent variables are same. Hence, I am using unstandardized coefficient, and where the unit of measurement are different, like you gave an example of attendance and so their attendance is measured in days, then 1 to 10 we measured the scale. So since the unit of measurement is different, we use standardized coefficient. Can I say that?
When you're writing interpretation, you don't write all those things. When you want to, after coming to coefficient value, first point you must say whether job experience is having significant impact or not. First point.
Okay.
Since significant value is less than 0.05, you say that job experience is impacting sales. Second point, job experience is significantly impacting. Independently, you write these 2 points first.
Okay.
After that, you are going to specify, since you said significant, third point you write it, job experience unstandardized coefficient is 1868.330. It means if 1 unit increase in job experience, sales will increase by 1868.330 units. Third point. Fourth point about education also. If 1 unit increase in job in education, then sales will increase by 598.220 units. Fourth point. Fifth point, job experience is impacting more than education by in terms of standardized coefficient beta value, because they are standardized values.
Okay.
And fifth point, you can talk about the intercept. Only these points.
Okay.
And you want to write regression equation. As the equation I have said, y is equal to a plus b1 x1 plus b2 x2. You can write that equation also. And you can complete the. And you can see this collinearity test, VIF value, multi-collinearity. What I said, what must be the VIF value? It must be
less than 5.
It should be less than 5. Then we say there is no multi-collinearity problem. And the case diagnostics. You can see this Mahalanobis value. Mahalanobis distance value. What is the value we got? 42.158. Okay. So 42.158 means you must go to chi-square value here. And you must say select P is equal to 001. 2 degree of freedom 2 you must see. The value is how much? 13.82. If you are interested in taking p value 0.05, it is still less. It is 5.99. But we don't have multivariate normality. Multivariate normality is violated. Multivariate normality is violated. Why? Because the Mahalanobis distance value, is very high here. For 42.158. And you want to identify which are those variables. Then you come here, you right click and say descending. Now, this is only the one variable which you need to delete.
Sir, could you please repeat, sir, please? This Mahalanobis right click.
That's it. Yeah, after, because already we have said Mahalanobis, you come here, right click and say descending. Sort it descending. Once you sort it descending, we'll see the highest value here. Only this is having a problem. This employee, this person is having only the problem because he's having very high experience and high education and he's contributing very high sales. So we need to delete this person because this is away from what you call as Mahalanobis wise outlier, that is. Okay. So this is how we are going to identify the outlier.
Sir, can you hear me, sir? I'm Shailendra speaking.
Yeah, please, sir.
Sir, actually, this if outliers I have like this and a lot of data I have, I cannot go to full data and find an outlier one by one and remove, right?
Not required. No, why
we should have an automated method. So, like you can use that interquartile range method, right?
Yes, interquartile
so that
range
can
also
be interquartile range directly you can use and remove all the outliers.
Right, that's what. But first of all, we need to decide whether outliers need to be deleted or not. We can identify outliers, sir. Because yesterday's session we have discussed about finding that interquartile range. I've shown you already our outliers method.
Yeah.
Already we discussed. Here I'm showing you something different. Here Mahalanobis
we can do otherwise we can do scaling or normalization. Then automatically these outliers will be taken care,
sir,
right?
When you do the scaling of normalization, that is not working, sir. That is only just only our satisfaction.
Okay,
that is
sir,
not going to work much. We have worked for that way, but that is not going to bring any sort of much difference for our data.
Okay, sir.
Log normalizing. So many methods we have used actually.
Yeah. Okay, sir.
Because we are
Okay.
not
Thank
able
you so
to
much.
see,
Thank you so much.
we're
Yeah.
not able to see much difference.
Yeah. Thank you.
So these are the assumptions which need to be satisfied. Now I'm closing this. Now after linear regression, we'll discuss about multinomial logistic regression. Now, earlier we said linear regression is used when you have dependent variable scale. But if the dependent variable is not scale, but if it is ordinal or categorical, then we must use logistic regression. Logistic regression. In this logistic regression also, binary is used when this nominal data, nominal level are exactly 2. Only 2. Then we are going to use binary logistic regression. When you have nominal more than, then we are going to use multi-nominal logistic regression. If the dependent variable is ordinal, then we are going to use ordinal logistic regression. Is it okay? So linear regression, dependent variable should be scale data. That is one. If the dependent variable is not scale, it is ordinal, then you must use ordinal logistic regression. In case dependent variable is nominal, then you must see how many levels are there in that. If it is exactly 2 levels, then we are going to use a binary logistic regression. If it is more than 2, then you must use multinomial logistic regression. Multinomial logistic regression. So this is a 3 different type of logistic regressions. So first let us do this binary logistic regression, where we have dependent variable is nominal or categorical, and they are more than, they are exactly 2 levels. So I'll take this example we have here. Sleeping case, this is sleeping problem with a binary logistic regression. You can see the data, I'll show you the data. This is the dependent variable, which is nominal. And it is more than 2 levels. Sorry, it's exactly 2 levels. Means we are asking the respondent, do you have sleeping problem? Yeah, if they say yes, 2, and no, they don't have any sleeping problem. And coming to the next, we have 3 independent variables: gender, age, gender, self-concept, and anxiety score. Okay, so these 4 are independent variables, and the sleeping problem is a dependent variable. So this dependent variable is having exactly 2 levels, which is nominal data. So in this case, we must use binary logistic regression. In this case, we must use binary logistic regression. Can I go ahead for the analysis?
Yes, sir.
And independent variables can be anything. It can be scale data, it can be ordinal data, it can be any data. But condition is only for dependent variable. Dependent variable should be nominal and only 2 levels. So I'll start the analysis. Analyze. In that regression, binary logistic. Right. Dependent variable is sleeping problem, and remaining all the 4 will take as covariates. Right. Can I go ahead?
Yes, sir.
Yes, sir.
Yeah. So click categories, categorical. In this, select gender as categorical covariates. Gender. Okay. Now in gender, 1 is given for male and 2 is given for female. So referential category will be the last one. Means we are going to discuss from female to male. Click continue. And in options, we need to select classification plot. Only classification plot will select as of now. Okay. We'll go for continue. And click OK. Can I click OK?
Yes, sir.
Please repeat about the option, sir.
Yeah. First, you must click this categorical. In this, because among all the 4 independent variables, only gender is categorical. So which is categorical, you bring from left side to right side. And in options, at the time being, we are only selecting classification plots. Click continue and click OK. Once I click OK, we will be in the output screen. Yeah. In this, you can see total we have 392 respondents and we don't have any missing data. Coding wise, 0 and 1. Dichotomous wise, it is coded. We have 1 and 2. 1 for no and 2 for yes. So here system made as 1. This is a referential. Means now we are going to say people who have sleeping problem with people who don't have sleeping problem. Now we can see this categorical variable coding also, male and female. Okay. Now you don't look for this block 0. Directly you must go to block 1. Now in this block 1, you must see this data summary. We discussed about R-square value, okay, in linear regression. In logistic regression, we call it as a pseudo R-square. Pseudo means similar, but not exact. So in this pseudo R-square, we have different type of parameters. Nagle-Kerek R-square must be taken. Nagle-Kerek R-square value. This value is 0.701. Same interpretation. What is the interpretation of R-square value? The amount of variance explained by the independent variables on the dependent variable. In the same case also, here Nagle-Kerek R-square, this value must be more than 0.7. We got near to 0.7 only, 0.701. Model summary. Right. Next is classification table. This is called as a confusion matrix. Okay. So how much the data able to explain or predict properly. People who are having no sleeping problem predicted as not having sleeping problem. 89.3% system has predicted. People who don't have sleeping problem, system predicted, yes, they don't have sleeping problem. The number of cases are 191. It is around 89.3%. People who are having sleeping problem predicted to be having sleeping problem are 88.8%. So this is also very good. Now total percentage of classification hit ratio is 89%. It should be more than 70%. Now fortunately we got here 89%. So this must be more than 70%. If it is less than 70%, the data cannot be used for further analysis. The data cannot be used for further analysis. So classification table, the overall percentage, which we call as hit ratio, is 89%. Can I go ahead?
Yes, sir.
Yeah. Now this is the interpretation which we did like unstandardized, standardized wise, but different way of interpretation. You can see age is not having significant impact on sleeping problem. Age is not having significant impact on sleeping problem. Gender also does not have significant impact on sleeping problem because these values are more than 0.05. It should be less than 0.05. Self-concept score is significant. So self-concept score has significant impact on sleeping problem. And even anxiety score is also having significant impact on sleeping problem. Now we can see here self-concept score is minus. In the sense, if self-concept increases, sleeping problem decreases. If self-concept increases, sleeping problem decreases. Anxiety is positive. If anxiety increases, sleeping problem will increase. If anxiety score increase, sleeping problem also will increase. So this is what is the interpretation for binary logistic regression. Binary logistic regression. Anyone have a doubt? You can ask at the moment. Hello?
No, sir.
Can I go for the next method?
Yes, sir.
Yeah. So in binary logistic regression, we have used dependent variable is nominal and exactly 2 levels. So this is the interpretation. Very important things are this classification table and these variables in the equation. You must see the significant value and you must interpret this B values. And next we will be discussing about multinomial logistic regression. In multinomial logistic regression, same like binary logistic regression, only difference is we are going to have more than 2 levels. We are going to have more than 2 levels. Let us go to the analysis. Yeah. Yeah, this is the data for multinomial logistic regression. We have 3 variables here: health problem, age categories, and exercise. If you see the data, health problem is the independent variable. It's a dependent variable. Sorry, health problem is a dependent variable. Age category and experience are independent variables. So we want to see how far this exercise and age categories are impacting health problems. And the statements you can see how we have asked. We have asked, do you get any health problem in the last 5 years? Did you get any health problem? So here they are asking they are giving a response in 3 levels. No health problem, critical health problems. Critical health problems they are having. Click OK. So here we can understand that dependent variable is nominal and it is more than 2 levels. It is more than 2 levels. So that's why we are using multinomial logistic regression. And independent variables can be anything. It can be a scale, it can be ordinal, it can be categorical. You can see age category, we have only 2 levels. Less than below 50 years and above 50 years. And coming to exercise, do you exercise regularly? 1 means yes, 2 means they're not exercising regularly. Now let's start the analysis. But for multinomial logistic regression, the condition is that the dependent variable is nominal and more than 2 levels. Like this case, here we have 3 levels. Hello, can I go ahead for the analysis?
Yes, sir.
Yep. Analyze regression in this multinomial logistic regression. Analyze regression, multinomial logistic regression. Now, in this dependent variable, we need to select as, did you get health problem in the last 5 years? Yes. Now here, a referential category, which you want to take. You want to take the last critical health problem was it, that was taken as a reference. And these 2 independent variables are taken as factors. These 2 are taken as factors. Right? Now we are referring this with 3 levels. First one here is health problem, no health problem, medium health problem, critical health problem. So with critical health problem, we are comparing. That's why you can see health problem last is taken as a referential category. Now in statistics.
Sorry. We have to set that referential category, right?
Yeah. Correct. Which you want to identify, which you want to refer, you can select. For example, I can say people with no health problems, I can compare with people having health problem, normal, or having critical health.
Okay, sir.
So we are here taking with having critical health problem with the other. So here we are taking classification table and goodness of fit. These two are taken. Remaining all by default is there. I'm not doing any sort of settings. Only these two I'm selecting. Classification table and goodness of fit. Click continue. In statistics, I've selected those things. In statistics, I've selected classification table and goodness of fit. And yeah, nothing is required. Only this small setting I did in statistics. Classification table and goodness of fit I have selected. Click continue and click OK. Once I click OK, we are going to land in output screen. Yeah, this is output screen. You can see total number of people are 1,305. In that, people who are not having health problem are 343. People who are having health problem of 106. Critical health problem 502 members are there. So you can see age category wise also below and above 50 years, and exercise also 695 people are not exercising, 610 members are exercising. Now coming to this model fit. Model fit, actually we have a null hypothesis. There is no significant difference between base model to the final model. In a simple sense, we want to say if this must be less than 0.05. This must be less than 0.05, then only we can go ahead. In case, if this is more than 0.05, we cannot discuss further. Means whatever results you are going to get, that is not going to have any validity. So you must see that the significant value must be less than 0.05. Is it okay? Yeah.
Yes, sir.
Goodness of fit value, this PSN value, this must be more than 0.05. This value must be more than 0.05. These conditions must be satisfied. After that, pseudo R square, neglect correct value. We got 0.343. Actually, this must be more than 0.7, we said. Okay, but here we have only two independent variables. That may be the problem. So if you increase the number of independent variables, there is a chance that this pseudo R square can increase. Now coming to the main analysis, you can see this analysis. Yeah. Shall I discuss these values?
Yes, sir.
Right. Now, this is important point where we need to see compared to critical health problem to no health problem. People who are healthy, no health problem. If you see age category wise, age category 2 compared to age category 1 is significant. It means compared to critical health problem, people who don't have health problem, there is a difference between people who are below 50 years to above 50 years. There is a difference between people who are age category less than 50 years to above 50 years. There is a significant difference between people who are having critical health problem to no critical health problem. And one more thing, it is positive. It is positive means compared to critical health problem, no health problem people are 0.892 times more in less than 50 years. Less than 50 years. Less than 50 years, people are more. That is positive because positive means are increasing. Compared to above 50 years, less than 50 years, people are more significant, more 0.892 units. And comparing to exercise, people who are regularly exercising compared to them, people who are not exercising. Just a moment. 1 and 2 means you must see what is 1 and 2. Just a moment. 1 means people who are exercising, 2 means who people are not exercising. Yes. People who are not exercising, people who are having exercising have good health, no health problems. This is positive. Critical problem, compared to critical problem, people who are having healthy are more in people who are exercising. People who are exercising, they are positive. 0.778. This is positive. Means compared to people who are not exercising to people who are exercising are having good health. It means simple language. People who are below 50 years are healthy, no health problem, and people who are exercising are healthy. And there is a significant difference between critical health to no health problem. These two are significant. These two are significant. In the same way, if you see critical health to normal health problems, people who are below 50 years compared to them, this is a negative, means that they don't have much health problems. This is reducing, this is getting minus. It means there are less people in this, there's less people in this. But comparing to exercising, it is not significant. This is not significant. Means there is no much significant difference between critical health problem to health problem in terms of exercise. In terms of exercise. But in terms of age, there is a significant difference. So this is the interpretation for multi-nominal logistic regression. Anything you want to ask, you can ask at this moment. Hello. Can I go to the next model? Next method?
Yes, sir.
Yeah. Next method is ordinal logistic regression. We use ordinal logistic regression when the dependent variable is ordinal. Independent variable can be anything. Now coming to the FDP. Yeah, ordinal logistic. Let us see again sleeping type of data only you have taken. Here. Yeah. So we're asking the respondent quality of sleep they have. So the respondent is giving in ordinal form. Very poor quality of sleep. Poor quality of sleep. Neither poor or good. Good and very good sleep. So you can see that dependent variable is quality of sleep. And the respondent is giving options and a ordinal data. So this is a dependent variable. Since the dependent variable is ordinal, we are using ordinal logistic regression. And there's two independent variables are there. Coffee they are drinking and anxiety levels. So coffee is also ordinal. You can see how much coffee they are drinking. Less than 5 cups per day, 6 to 10 cups, 11 to 15 and above 15. This is a European or maybe American, because generally in India, no one drinks more than 15 cups of coffee per day. So this is a European data. So they can drink more than 50 cups. They drink a very huge amount also. So this is related to coffee drinks. Anxiety, it is in a scale. So amount of anxiety they are feeling, I think they are given a scale on this. They need to rate it. Now we want to see what is the impact of coffee drinking and anxiety on quality of sleep. Here we are going to use ordinal logistic regression because the dependent variable is ordinal. Can I do the analysis?
Yes, sir.
Yeah. Analyze regression ordinal.
So could you go back, please?
Yeah. Here, dependent variable is quality of sleep. And we can take the two factors as factors. You can take anxiety as covariate, not a problem, because factor generally we take as which are nominal. So covariate you are taking as anxiety because this is a scale data. Independent variable can be anything. It can be dependent, it can be ordinal, nominal, scale. But a dependent only should be ordinal data. In the options, we have nothing to do in these options. And output, we want to see goodness of fit, scale. and all these things. I think this is perfect. We're not going to do any sort of setting here also. Okay, click OK. So I've not did any settings here. I've simply taken dependent variable as quality of sleep and factor, number of coffees as factor, and covariate as anxiety. So which are scale data you need to take into this box, which is called covariance. Click OK. Yep. I can see number of people. Total 99 people. 1 people is missing, it is saying. One data is missing. So very poor 20. Poor quality of sleep 54. Neither poor nor good 4 members. Very good 8. And very good is 13 members. You can see this all case summary. And as I said earlier also, for model fit information, the significant value must be less than 0.05. The null hypothesis is there is no difference between base model to final model. So which we need to reject that. And goodness of fit, this PSN value must be more than 0.05. So these 2 parameters are satisfied. In case you are not able to satisfy the condition, we cannot go for the further analysis. Here, pseudo R square, neglect correct value 0.434. It should be more than 0.7. The problem is we have only 2 independent variables. That's why these 2 independent variables are not able to properly predict the dependent variable. Now coming to parameter estimations. Now if you see here, in this case, anxiety is having significant impact on quality of sleep. 0.005. It is minus. In the sense, if anxiety increases, quality of sleep is decreasing. Quality of sleep is decreasing. You can note 1 is very poor, 5 is good quality, good. Very good quality of sleep they are getting. So minus means if anxiety is increasing, quality of sleep is decreasing. Now coming to this number of coffee they are drinking. People who are drinking very high amount, like more than 15 cups of coffee, are taken as a reference. So compared to extremely drinking coffee people who are drinking very minute is significant. And they have positive, means they have more good quality of sleep. More good quality of sleep. Anxiety, I said negative. If anxiety increases, quality of sleep is decreasing. Here, compared to people who are drinking very large amount of coffee, people who are drinking very minutely, they are having 3.530. Means they are having very good quality of sleep compared to people who are taking high consumption. But compared to very high volume, like 15 cups, to people who are drinking 5 cups or less than 5 cups, see, the impact has reduced, quality of sleep has reduced. Because these people are also taking maybe like 5 to 6 cups they are taking, 5 to 10 cups they are taking the coffee. Okay, so this impact has reduced 1.38. But people who are drinking high amount of coffee to people who are drinking 10 to 15 cups, there is no significant. Means where they are drinking 10 to 15 or above 15, there is no difference in the quality of sleep. That is not significant. That is not significant. So because the significant value is 0.583, this is not significant. So in this way, we can understand what is the impact of coffee and anxiety. If anxiety increases, quality of sleep decreases. And already I have explained you must take a reference of coffee drinks 4. Coffee drinks 4 means coffee people are drinking more than 15 cups per day. Compared to people who are not drinking coffee, people are drinking moderately and people are drinking in a high moderately, like 10 to 15 cups. Any doubts are there? You can ask at the moment because this is the last topic in this series. Hello? Hello?
Hello.
Yeah.
So just
Any
the
doubts
first
are there? You
step.
can ask at the moment. If not, we can conclude the session here.
So just the first step, analysis, ordinal, no?
Yeah. Please ask again.
So the first step of analysis, just navigate this kindly, please, if you can. Analysis.
You want to say about the ordinal logistic regression?
Ordinal, yes, ordinal. Sir.
Yeah, I'll just show you once again. Yeah, we have first step. We are talking about that this case summary. You can write it, all the case
So
summary.
not this
After
one.
that,
So not
yeah,
the
yeah.
interpretation. The first step when you go to analyze and when you
okay. You're saying process
navigation.
of analysis.
Yeah.
Navigation. Analyze in that regression, right? In that ordinal.
Okay, sir. Thank you.
Right. Yeah. Any more doubts we have, we can ask. So in the total process, we have discussed all these topics, starting from basic of SPSS. Okay, we discussed our missing data. We discussed our hypothesis, normality, type 1, parametric, non-parametric, one sample t-test, two independent sample, data homogeneity, paired sample t-test, chi-square test, and we discussed about one-way ANOVA, one-way repeated measure ANOVA, two-way ANOVA, MANOVA, and we discussed about correlation, linear regressions we discussed, and we discussed about the logistic regression, all the three types. And we concentrated more on the assumptions for MANOVA and regression. Why? Because this is very extreme cases for multivariate data analysis subject.